This is a quick video example on finding the derivative of an exponential function of base e. So when we look at this function, when I input a value into the function, that input is being sent to the exponent. And both of these exponents have a base e. So this is an exponential function, base e. That means we're going to follow our base e derivative rule that looks like this. So I'm just going to write the most generic possible exponential function I can with base e. I'm going to write base e, and I'm going to write the exponent as a function. Okay. Now the parent function would have an exponent that's just a plain x there, but to generalize this, I'm going to write my exponent as some function. So my exponent could be a linear function, quadratic function, it could be all kinds of stuff. It's just the exponent is some kind of function. And when I take the derivative of that, the rule tells me I rewrite e to the exponent that's given to me exactly as it's given, but then I have to tack on the derivative of the exponent. That's called the chain rule, when we tack on the derivative of the exponent there. But when we look at this rule, the basic pieces of this rule here, we have e to the exponent in the original equation or the original function, and we see the exact same base e and exponent in the derivative. But then we're tacking on the derivative of that exponent. So let's apply this rule to the function we were given. Oh, and before we do that though, let me just come back here to this basic generic rule here. So there's an understood coefficient of 1 in front of that base e, right? And there's an understood coefficient of 1 in the derivative as well. So we could rewrite this to say if there's any constant coefficient in front of that base, that constant coefficient is going to carry down there to our derivative. And I'm just pointing that out because in the first term of my function here, I see that there's a constant coefficient 5 in front of the base e. So when I take the derivative, that constant coefficient 5 is going to carry down to the derivative as well. So let's go ahead and do that. So let's take the derivative of this function. So I'm using my f prime notation now because I'm going to apply this generic exponential function base e rule. So my rule says I'm going to rewrite the constant coefficient, the base e to the exponent that's given to me, but then I need to tack on the derivative of that exponent. So let me move that over a little bit so I have some more room to write here, and I'll write out what I just did in words. Okay, so what did I just do there? I rewrote my constant coefficient, I rewrote the base e, I rewrote the exponent, so rewrite the exponent, and then I tacked on the derivative of the exponent. Derivative of the exponent. Okay, and then we'll just do that for the second term here in the function. So this term has an understood coefficient of 1 in front of the e, so we don't have to write it. But technically that understood coefficient of 1 is carrying down here to the derivative. You don't have to write that. But I'm going to rewrite the base e. I'm going to rewrite the exponent exactly like I see it. And then I'm going to tack on the derivative of that exponent. Now, deriving this rule or understanding where it comes from is beyond the scope of this course. You can do take the limit of the difference quotient of an exponential function and do all that algebra, and you'll see that this rule is true. In this class, you just have to know the rule and be able to apply it. So you're using that derivative rule as a template. We're basically saying that if our equation or our function fits this pattern for this exponential function that's base e, if it fits that pattern, then you can find the derivative by following this template. And again, you don't have to understand where that rule came from or why it works. You just have to know how to apply it. And that's what I did here. I kept the base exactly like I saw it. I rewrote my exponent exactly as it was given, just like I'm told to do here, right? So when I come back, I rewrote base e in my generic rule. Then I rewrote the exponent exactly like it was given. But then my generic rule says tack on the derivative of the exponent, and that's what I did here. I just tacked on the derivative of that exponent. And then I applied that template again. I rewrote the base e. I rewrote the exponent exactly as it was given to me. And then I tacked on the derivative of the exponent. So this is the calculus. I'm following this template. I'm applying this rule. Now we just need to clean this up a little bit. So rewriting this first term, I have 5 base e to the negative 8x power, and then the derivative of negative 8x. I just follow my power rule for this because this derivative happens to be a polynomial function. It's a linear function. I'm going to follow my power rule, and if you do that, you get a derivative of negative 8. Plus, in the next one, I rewrite e to the 6x power. And then again, I'm going to apply my power rule when I'm finding the derivative of that exponent, because 6x is a polynomial. It's a monomial. It happens to be linear. The derivative of 6x is just 6. And again, for both of those, I'm just using my power rule. There was an understood 1 exponent. So I multiplied my exponent times the coefficient. That gave me the 6. I rewrite the base and decrease that exponent by 1, but that gives me an exponent of 0. And then when I tack on the derivative of base x, the derivative of x is just 1. And x to the 0 power is also just 1. So I ended up doing 6 times 1 times 1, which is just 6. But at this point, you might recognize that when your base is a plain variable, in this case, a plain x, you don't have to apply the chain rule. Technically, you're applying the chain rule, but it turns out the derivative of the base is 1. You don't really need it. So you might have weaned yourself or gotten to yourself to a point where you recognize that. If not, just follow your chain rule. And same thing I did here on this exponent. And, it's power rule. There's an understood exponent of 1. I multiplied the exponent by the coefficient. That's where I got the negative 8. I would rewrite my base and decrease the exponent by 1, which would give me an exponent of 0. And then I would tack on the derivative of the base. But x to the 0 power is 1. The derivative of x is 1. Negative 8 times 1 times 1 is just negative 8. So all those extra steps there, when you really internalize this, they're not necessary, but you can totally do them. And then I can clean this up a little bit more. There's 1 or 2 more things I can do here. In this first term, I have 5 being multiplied to e to the negative 8x being multiplied to negative 8. And since order doesn't matter when I multiply, I can go ahead and multiply that 5 and negative 8. So I'm going to do that here. Multiplying that together, I'm going to get negative 40, and I'll just write that in front of the base e to the negative 8x. It just order doesn't matter when I multiply, so I put the constant number first and the exponential part second. And then for my second term here, there's not really much I can do. I can rewrite it to put this constant 6 first and the e to the 6x second. And you can stop here. You don't have to do anything else. Unless you're asked to factor out a GCF or do further steps, you're done. This is our derivative of the original function that was given to us. And again, what this means is if I give you any x coordinate, okay, so if I gave you, x equals 2, and I plug it into my original function, that original function is telling me where the ordered pair is located on the graph. And I'm just making this up. Let's say the ordered pair was located right there. So I would have some kind of exponential function, and my ordered pair would be located there, just pretending. And then if I plug 2 into the derivative, that's telling me the slope of the tangent line at that point, or the instantaneous rate of change at that point where x is equal to 2. So original function tells you all the points on the graph. The derivative tells you the rate of change of those points at that specific point on the graph. Okay, if you have any follow-up questions, don't hesitate to email me. I am happy to help.